Magnetic flux. Magnetic flux we will calculate in the same way as we calculated before the flux of electric field. Definition of magnetic flux is the integral from magnetic flux density ds. This is the flux through surface S, and here we have dot product. So if we have magnetic line, for example, we have magnetic line, and here is the surface S. First we should define vector ds, and we defined this vector according the right hand screw. So if the direction of this curve is like that, according to, no, it should be direction like that. So in this case the surface is defined, vector of surface is defined in this direction, and we have positive flux. And now we can write the law, Gauss law, for magnetic field. Gauss law for magnetic field integral over closed surface S is B ds is equal 0. So what's that mean? That means that we doesn't have the source of magnetic field where magnetic line starts or end. Magnetic line can be only like a closed loop. So every magnetic line will be closed. It creates a closed loop. And let's write what we have here. Magnetic flux passing any closed passing through any closed surface is equal to 0. Using the Gauss-Ostrogradski-Green theorem, we can find derivative or point form. This is integral form. Of Gauss law, and point form of Gauss law that divergence of B is equal to 0, and the boundary condition Bn2 minus Bn1 is equal to 0. So we see that there is a difference between the Gauss law for electric field, where we have here Q and here is the magnetic induction, electric induction for electric field. For magnetic field it is equal to 0, so it is simple to remember as well this law. And how we can explain this? We can have, this is a closed surface. We just closed surface. We have closed surface, and magnetic line can go through this surface in two ways. In such a way that they enter so here we have minus phi and here is pure phi, because the surface is closed surface is defined always outside of the surface. So this is positive, this is negative, and here we have positive. And we have as well loop that do not cross through our surface. They are entire in the surface. This two case. We see that we doesn't have the source of magnetic field. That means we doesn't have points where magnetic field starts or where magnetic field finished. When magnetic field line finish. Magnetic field in materials. Up to now, we learned that the source of magnetic field is the element with current. So from such element we have induction B. But here I have the example of magnet, and we see that we doesn't have any current here. I do not have supply for this, but as you see, this is the magnet that show us the force, magnet force. And now I try to explain how it is possible. Without current, we have magnetic field. Let's start with, let's have small loop with current, and we defined the vector of magnetic dipole momentum. magnetic dipole momentum. The definition of this vector is if we have the loop with surface S and vector M is equal current that pass through in the loop multiplied by current multiplied by vector of surface. The direction of vector we choose according to the rule of right hand screw. So we rotate over the loop in the way to show that the right hand screw will go in this direction. So the direction of vector M is like that. And this is ampere multiplied by, the unit is ampere multiplied by meter square. And now, when we put such magnetic dipole momentum, we can say that this is a magnetic dipole. So if we put such dipole in magnetic field, let's have magnetic field. And here we have magnetic dipole. Current has this direction. We will have the force that tends to put the dipole, magnetic dipole momentum parallel to the magnetic field. So here is magnetic field, and the force try to put this magnetic dipole parallel to the magnetic field. Torque or mechanical moment can be written torque can be written as a torque is equal to magnetic dipole momentum multiplied by B. Magnetic dipole momentum multiplied by B. Mechanically we can write it this is the same. You can find as well in this way. And if we have such dipole, in the way put it in the way that this vector is opposite to the magnetic field, we can say that we have potential energy, maximum of potential energy, and this potential energy can be used to make a work. And this potential energy is written with formula M multiplied by B. As is, if you remember, these two formulas are very similar to the formulas for electric dipole. We have here for magnetic dipole. And this is in joule, and this is in joule. And now we defined vector of magnetization. Vector of magnetization. Vector of magnetization. If you have a piece of material that is put in a magnetic field B, and if you have magnetic dipole in this material, each of magnetic dipole have its vector ME, its vector of magnetic momentum. And now well, let's have here one. If we take into consideration the component that is parallel to the E is the direction of magnetic field, this is ME. Vector of magnetization is defined as a sum of ME over each E, where ME are the component parallel to the direction E, direction A, and divided by delta phi. So we can say that this is the density of magnetic dipole. This is a density of magnetic dipole. This is the sum over all E. And the unit of this vector of magnetization is ampere divided by meter. And if the value of this vector is different than 0, we have magnetized material, like this example. And now I have to explain why without the current we have permanent magnet. This is because in this material, in the crystal rate of this material, we have such currents between the atoms. We have the free electron that rotate, for example, like that. And the surface of rotation is similar. So the sum of vector of dipole of magnet dipole give us vector of magnetization. And this explains why without power supply, without current, external current that pass through this magnet, we have magnetization, vector of magnetization. And now we will define the magnetic field strength or magnetic field intensity. Magnetic field intensity, magnetic field strength. Definition. We have definition of magnetic field. This is the vector, and we always use letter H for this value, and the unit is ampere divided by meters. In materials, if you have materials, vector of magnetization is proportional to the magnetic field strength. So if we have here magnetic field strength, now we can write that this is H. Vector of magnetization M is proportional to magnetic field intensity. We have to remember that this proportionality is not perfect. We can say that this is not proportional, but for the to simplify the description of magnetic field, we take we write that it is proportional. Theta m is the coefficient of proportionality. So it doesn't have unit, and it is called magnetic susceptibility. Magnetic susceptibility. And now, and this I tell you one more time, it doesn't have unit, it is coefficient of proportionality. And we write this to our definition. H is equal to B divided by B0 minus theta m H. So from this we have 1 pu theta m multiplied by H. I put this on the left side of the equation, is equal to B divided by B0. So finally we have that B is equal B0 1 pu theta m H, and finally B0 BR H. This formula is much easier to remember, than this one. So, and where R is relative magnetic relative permeability, relative permeability mi R, where mi0 is absolute. Mi0 is absolute permeability. Regarding the unit of magnetic field strength, one can find in American books the unit that is called Ersted. Ersted is equal 10 to 3 divided by 4 p ampere divided by meter, and this is 79 and 6. 1 Ersted is 79 and 6 ampere divided by meter. Ampere by meter is the SI unit, but in America they use Ersted. It creates problem when the team of scientists have to cooperate with teams from America. For example, when they project space devices, and it happens that that vehicle that should work on the moon doesn't work because of this misunderstanding of the units. And now, how we divide the materials. We divide materials in 3 main groups: paramagnetics, diamagnetics, and ferromagnetics. Let's write the difference and the value of the parameter of relative permeability for exemplary of each of group. Materials we can divide in 3 groups: diamagnetic, paramagnetic, and ferromagnetics. Diamagnetics are materials where we doesn't have magnetic dipole. So if we doesn't have magnetic dipole, we can't have as well vector of magnetization, because this is a sum of the magnetic dipole. And now the next, and here is the example of such material: copper, silver, and water. We see that magnetic permeability is slightly less than 1. The difference is very small, and for all materials we see that this is similar case. Diamagnetics are repelled by magnetic field, but the force of repellation is not very strong. Paramagnetics are materials where we have magnetic dipole, so magnetic dipole is different than 0, but we can't have magnetization, because we can't obtain the orientation, stable orientation of the magnetic dipole in the same direction. Of course, this is for all gases, for gas, and air is an example. And we see that for air we have relative magnetic permeability slightly different than 1, a little bit higher than 1. The same for aluminium, the same for platinum. Please remember that aluminium is not ferromagnetic. Aluminium is paramagnetic, so we can't, it is forbidden to make magnetic shielding for magnetic field with the use of aluminium, because such shielding doesn't work. Paramagnetic material are attracted by magnetic field, but the force of these forces are very, very weak. Ferromagnetics. Ferromagnetics are the most important from technical point of view, so I will tell you more about ferromagnetics. Ferromagnetics we can divide into group. This is the so-called soft and hard ferromagnetic. I'll explain you where is the difference. How ferromagnetics are constructed. Let's have ferromagnetic like steel, like ferro. Ferro is the name that comes from Greek, because the phenomenon of magnetic was noticed that for the mineral of ferro. And how this material is constructed. It has crystal domain that are as well magnetic domain. So this is the crystal. The volume of this crystal domain depends on the purity of the material. When the material is pure, without addition of another material, this domain are bigger. And in each domain, the direction of magnetic dipole, all dipole have the same direction. For example, like that. And if we apply to such material magnetic field, the dipoles start to move according to obtain direction according to the direction of the field. Let's have it in this direction. At the beginning, the action is very weak, so we have vector of magnetization is here is the vector of magnetization, and at the beginning the response is weak, and if we take off magnetic field, it came to zero, because it moves slightly, and if we remove the magnetic field, it return to the same position from which we start. But in some moment, for certain value of magnetic field intensity, we see a strange, very deep, very strong response of magnetization due to magnetic field intensity. That's happened because this is magnetic domain, in magnetic domain, the magnetic dipole switch all together to the direction parallel to magnetic field. So the process starts here, that in domain the direction of magnetic dipole switch to the direction of magnetic field. So we have very strong response of magnetization due to magnetic field intensity. And when all domains are parallel to the magnetic field, we have saturation. This curve is called primary magnetization curve. Primary magnetization curve, and when we take off magnetic field, it do not return in the same way. It returns like this. So the position of dipole that we obtain with the magnetic field remain in the same direction. And here we have the magnetization that remained. And this is the remittance residual induction. Or we have here magnetization, residual magnetization. So if we change from one direction to another, we obtain the hysteresis. And I will show you the hysteresis curve. Hysteresis loop. Here is primary magnetization curve, and when we change the magnetic field intensity, when we go down with magnetic field intensity, we do not return in the same way, but we goes here. And after changing the direction, we have such curve, and after we came back. We have characteristic point. Here is the point that we call remaining residual induction. And second point, coercion. We can calculate what corresponds to correction. We see that magnetic field is equal to 0. This is equal to 0. So we see that induction is equal to 0. This is equal to 0 at this point. So you see that H is equal to vector of magnetization. So, to cancel magnetization, we have to apply such value of magnetic field. For this point, in value of H is equal to 0. So we can write that 0 is equal B divided by mu0 minus M, so M is equal B divided by mu0. So this decides how strong is the magnet, because it tells us about the vector of magnetization. And we can divide ferromagnetic material in two groups: soft material and hard. Soft material have very thin hysteresis loop, and these materials are used for transformer, motor cores, and similar application. When we need material that doesn't have big vector of magnetization. This material, hard ferromagnetics, have such hysteresis loop, and this is mainly permanent magnet. For example, this is an example of such hard ferromagnetic. And we have to remember the different field of application of soft and hard ferromagnetic material. And what is important for magnetic material? We have to remember that this material, that value of relative permeability is not constant. If we calculate the value of r, in this point it will be maximum, and here it is going to be 1. If we made a sketch of dependence of r to the magnetic field intensity, we find that it starts here, obtain maximum, and after fall down. This is the initial value, r initial. Here we have maximum, and when we obtain saturation, it falls down. So for magnetic instrument devices, for magnetic devices, we have to remember that r is not linear, and we have to remember to project the work point for devices in this band, in this sector, because if we will find display, if our magnetic field intensity will obtain saturation, then we have a lot of non-linearity. For example, from transformer we obtain something like this. So we should have something like this, but because of non-linearity, when the point of work of transformer is in saturation, we will have such not non-linear. This is not sinusoidal curve on the secondary circuit of transformer. Every ferromagnetic have a particular temperature when it loses its ferromagnetism. It became paramagnetic. And this point was discovered by Curie, and for nickel it is 360, for cobalt 770, and for iron 1130. This temperature is much lower than temperature of melting, and the ferromagnetic feature finished at this temperature. And I would like to show you some example of ferromagnetics. Here we have soft ferromagnetics and here hard ferromagnetic. We start with soft material that we use to construct transformer, rod of motor, where the most important is a very small coercion. Coercion should be as small as possible. This is important because the surface of hysteresis curve decide on power losses for remagnetization when we change the direction of the field. The power losses depends on the surface of hysteresis curve. In this case, when the coercion is very small, the surface of hysteresis is small. We see that for pure iron we have very high value of relative permeability, magnetic permeability, and it is 2 million, more than 2,750,000, and that means that even for very little magnetic field we obtain saturation very quickly. Maximum induction that we can obtain is 2.15 Tesla, and for most material this is the limit. 2 and something is the maximum magnetic field that we can obtain. The stronger field we can obtain with superconductors. With superconductors we can obtain up to 50. The world record is 50, and in Poland we have, in Wrocław, we have 20 Tesla magnet. And now we see how very little addition of another material change the mir initial and mir maximum. We see that from 2 million it fall down to 5,500. So even very small addition of another materials to the iron dramatically fall down magnetic permeability. And hard material that are mainly used for different kind of application, permanent magnet. The first one materials that was artificially made, technically made, was alnico. It was in 1930, and it helps to construct radar. Thanks to this the discovery of this material, alnico, it was possible to construct radar. Because the magnetron, the lamp that is called magnetron, was constructed with this permanent magnet. But the strength of this material is little. This is the maximum magnetic energy per square by centimeter up to power to third power. This is density of energy in this material is only 0.056 joule by centimeter to the third power. In the years of 50, ferrite was developed. It is less strong, but it is not so heavy like alnico. So for some application, the ferrite was used. And in year 16, cobalt permanent magnet were developed, were invented, but it was top secret material. NASA invented this material, and today this is the commonly used material. This is an example of such material. We see how strong it is. It is very difficult to put it away. And this is neodyne. This neodyne, it is covered with nickel. And when you broke such materials, please throw it away, because neodyne material is dangerous for the health. So when the magnet is broken, please throw it away. So today, neodyne material is commonly used for permanent magnet. Ampere's circuital law. This law could be derived from Biot-Savart law, and it is very useful for calculation, for solution of magnetic circuits. What is the circulation of magnetic field intensity over closed loop is equal to the sum of the current surrounded by this loop. So, if we have loop like this, and this loop surrounds wire with currents. Let's have one I2 and I3. According to this law, circulation of along this path, this loop, in each point we should have value of magnetic field intensity. For our case is equal to I1 minus I2 pure I3. Why this two with pure and this with minus? We take to the formula current with plus if the direction of current is connected with the direction of the on the loop with the rule of right hand screw. So we see if we take a right hand screw, we turn it according to the direction of the loop. So current 1 will be taken with plus, and current 3 will be taken with plus, when current 2 will be taken, should be taken with minus. This formula can be written in the point form. Cross product of H is equal to vector electric current density. And now let's apply this formula. We see how easy is to obtain the result for some cases using the Ampere's circuitral law. During the exercise we calculate the magnetic field intensity from straight line with current. Let's have such line. With current I in this direction. Magnetic field creates such line, and direction of this magnetic line is like that. And now using we calculate the magnetic field intensity at the distance of R from the wire with current. So we write this formula, ADL, HDL, and now our loop will be parallel to the line of magnetic field. We take this loop that is parallel to magnetic field. So H is parallel to GL, and because of symmetry, magnetic field intensity on this curve is constant. So we can put this before our integral, and here we have unit integral, unit line integral. So we know that the result of this integral is the length of curve L. So is h multiplied by 2 pi r. We can write this as a function, so I write this with small r. And the right side of the equation is equal to I, to current. From this we see that we have function I divided by 2 pi r, and for magnetic flux density we have μ0 I 2 pi r. This is in vacuum, in air, because we doesn't have relative permeability is equal to 1. Using the Ampere law, our calculations are very simple. And this law, Ampere circuital law, is used to find solution in magnetic circuit. But when we can apply Ampere circuital law, we can apply it for constant current. And we can as well apply this for alternative current, but we have to remember that the frequency, from frequency we can calculate lambda, the length of the electromagnetic wave. And the circuit, we can apply Ampere circuital law when the biggest dimension of the circuit are smaller than, we can write this, is smaller than lambda. So lambda should be much bigger than dimension of the circuit. For 50 Hertz, it doesn't matter, because for this frequency lambda is 6,000 kilometers. So for magnetic board, for normal magnetic devices, 6,000 kilometers is much bigger than the dimension of the magnetic devices. Electromagnetic induction. We know that on the charges moving in magnetic field is exerted force that is called Lorentz force. And now, what's happened if we have charges in conductor? So conductor moving in magnetic field. And we have here the magnetic field that is perpendicular to the board, and in this magnetic field that is uniform perpendicular to the board, we move the conductor with velocity v. According to the Lorentz force equation, on charge, on positive charge, that we have here in the conductor is exerted force according to this equation. So let's find the direction of this force. We see that V is in this direction, so this is first. And B is perpendicular to the force in this direction. And now we rotate V on B. So direction of the force, this force, is up. So on each of this charge, Lorentz force is exerted. And now if we close the circuit and put here milliampere, we notice that we obtain the current. From the beginning of magnetic field to the end of magnetic field, current flow through this circuit. This phenomenon is called electromagnetic induction. So we have electromagnetic induction, and how we can call it. This is a phenomenon of the occurrence of EFM in moving in the magnetic field conductor. EFM we have here, because here we have Q and here is minus. The value of EFM can be calculated from formula. We know that formula for EFM is the integral over the vector, electromotive vector d from, we can write it from 1 to 2. Electromotive vector we can write as a Lorentz force divided by Lorentz force divided by Q multiplied by dl. So we have integral from 1 to 2. V multiplied by B, because Q is reduced, the dl. And this is the EF electromotive force. For our case, this is the simplest possible situation, where we have a conductor that is which length is L. This conductor moves with constant velocity V in constant magnetic field. So is equal V multiplied by R and L. This is the EFM in volts. But this formula is difficult to apply for all possible situations, because EFM we can obtain as well, for example, if we have a frame and dimension of this frame are growing. In this case, we as well obtain EFM, or we have the frame and this frame rotate, change the surface according to magnetic field. In this case, we as well obtain EFM. How to write the equation that describes such case? For example, that we have the frame here that rotates in magnetic field. We have frame, and this frame rotates in this axis. Let's try to develop such formula. Let's have magnetic field perpendicular to the board, and we place in this field the frame with one arm moving. So this is the 1, 2, 3, 4 arm placed in uniform magnetic field. This field is perpendicular to the board, and this arm of the frame moves with velocity v. According to our formula that we obtained before, EFM is equal to VB and multiplied by L. So we analyze, let's take direction of analysis of this circuit. EFM will be equal V. We have simple case because velocity is perpendicular to the direction of the magnetic field. So we have phi1 b dl pu phi2 b dl pu phi3 b dl and pu phi4 b dl. In this way we have the closed circuit, and we see at once that phi2, phi3 and phi4 is equal to 0. So this part is equal to 0, this part is equal to 0, and this is equal to 0. And now let's analyze this circuit. What will be the direction of, because we want to leave the vector, so we have to write the direction of EFM. We have B in this direction, V in this direction, and we rotate V over B in this way. So we see that EFM will have such direction. Now we write that this is equal V multiplied by B and multiplied by L. V, we doesn't have vector anymore, and minus means that the direction is opposite to our direction of analysis of the circuit. V can be written as the x divided by dt B L. And now the x multiplied by B, I write it one more time, L multiplied by the x divided by dt. This is the change of the surface of the circuit. This can be written as a ds. So we have minus B ds divided by dt. And BDS is the change of the flux. D phi B divided by dt. So we see that electromotive force is equal dVB divided by dt. And this is a very important formula. That can be applied to find EFM, electromotive force, for any case. Where we apply this phenomenon, where we apply, I mean technically where we apply. It is used in generator of current. In generator of current, we change the flux passing through the frame, and this frame rotates in magnetic field, so we obtain the EFM on the connection of the frame. And the frequency, of course, the EFM changes with the frequency of the rotation of the frame. And if we have the frequency of rotation equal to 50 Hz, we'll have generator of alternative current with the frequency of 50 Hz. And this phenomenon was discovered by Faraday, and this is called Faraday law. Faraday law. Faraday discovered that in moving in magnetic field conductor, we have electromotive force. But what about the places where we doesn't have the circuit, closed circuit? And Faraday discussed discuss his discovery with Maxwell, and Maxwell answer what's happened with in the volume where we doesn't have the conductor. I explain this better in the case. We have permanent, let's write it black. We have permanent circuit, and we change, and this here we have the magnetic field that changes the phi b divided by dt. According to the law Faraday's law, we will have here the EFF, current, that pass. This is conductor. But what about the field here? And Maxwell make big invention, big addition to the Faraday law. Faraday law was in 1931, and Faraday add to this law, on the left side of this law, he wrote that and this equation is called Maxwell Faraday, because what happened? Faraday suggests that around this changing magnetic field, we have new kind of electric field. We have here circular electric field. Here is the electric field. Up to now we know that electric field start at positive charges and end of the line of electric field start at positive charge and end of negative charge. And now we see that we have vortex here, new kind of electric field that are close, that create a closed loop. In the place where we have conductor, we have currents, because from this we can this is the electromotive force, and when we apply electromotive force to the conductor, we obtain current. So in closed loop of conductor we will have current, but in the place surrounding changing magnetic field we have vortex of electric field, new kind of it was very important. This discovery was very important, and thanks to this, Maxwell was able to create his 4 Maxwell equation, the main equation that describe electromagnetic field. But before we go to the Maxwell-Faraday equation, let's try to find the direction of the inducted current in this circuit. At the beginning it is difficult to say, but we can apply the rule that is called Lenz's rule. Lenz's rule. What is saying Lenz's rule? Lenz's rule say that magnetic field created by inducted current try to be opposite against magnetic field that it created. How it looks? Let's have this the same case, and we have the same magnetic field. But let's phi b is growing. So induction, if the dimension of circuit remain the same, induction is growing. What's happened? According to the Lenz's rule, I write it one more time. The inducted currents created new magnetic field that will be opposite to the magnetic that create our current. So if it is growing, the inducted magnetic field will have this direction, because it grows, but direction of this try to damp this growing. So such magnetic field will be result of the inducted current that flow in this direction. So the direction is like that. One more time I will explain one more time. Magnetic field is growing. So inducted currents create magnetic field that damp this growing. So direction of this inducted, this is phi b inducted, is like that. And we see that such current will create this magnetic field. Another example. Let's have the same circuit, the same direction of magnetic field. And now magnetic field is going to be smaller. In this case, inducted magnetic field will have such direction. Because if this magnetic field is going to be lower, it tries to support the main magnetic field. In this case, the direction of inducted current will be like that. When magnetic field is going to be lower, inducted magnetic field try to support going down magnetic field, so inducted current will have such direction. Length's rule is very useful. We always can find the direction of inducted currents using Length's rule. In every case when we have electromagnetic induction. And now let's return to Maxwell-Faraday equation. This is one of Maxwell four law, and I will write it one more time. So, circulation of electric field is equal to magnetic flux changes in time. We can write this. This is circular. No, this is the integral form and point or differential form of this law. Carl and boundary condition remain the same like for electrostatic. And how we can make the picture of this? This is the L, and here we write minus. Minus the changes of the flux through this surface the flux of magnetic field is equal to the electromotive force over the closed loop L. And direction depends on the Lenz rule. It depends if this flux is growing or is damping. Maxwell-Faraday equation is one of the four equation of Maxwell, and it is called in equation of Maxwell is called Faraday equation. This is very electromagnetic induction is very important invention because it allows to use the produce of electric energy. The generator of today's plant for production of electric energy using this law.